I'd like to talk about education from a systems perspective. At NSF, we tend to fund individual faculty to do different types of projects in research and education, and we try to encourage faculty to integrate their research results into the classroom. We spend well over $700 million a year at NSF to faculty to award different types of education-related projects. And yet we still have the conversation today, as we did even a few years ago, about concerns over the science and engineering pipeline of students. In some industry sectors, for example, aerospace engineering, I hear from companies like Boeing and Raytheon and other types of companies related to the aerospace industry who are required to hire US citizens, but we now have a global economy, a global perspective, and this country is just rich with talent from all across the world. But not everyone can work at Raytheon, and not everyone can work at Lockheed. So we have an issue about US citizens. And then just getting students engaged into this whole science and engineering ecosystem is a challenge, as you know, and I am a mother of one son. And so I understand that issue. So let me offer a systems perspective in this discussion. Okay, so first I'm going to highlight the current situation that we're talking about at NSF, and then move on to what we think, or we're talking about around the people we need to engage in education in this general area, and then offer an idea of how perhaps we can move forward in a partnership. First of all, let me show you a couple of slides about the current situation. We talk about, in the United States, offshoring quite a bit, and I know some of you are from other countries, and perhaps some of our sectors have moved to your country, which is just fine. It's important to know what this dynamic is. So in the US, we were leaders in exporting in these different technology areas as well as some others. But around the year 2000, the switch took place where we tend to import more than we export. We are in a global recession at this time. I'd like to point out that back in the 80s, 70s and 80s, it did not take very long to recover from a recession, perhaps a year, maybe in some cases half a year. And so we move into the 80s and 90s, and we see that the curve is starting to broaden, where the recovery is taking more time. We move into the 90s, and look at this recovery period. The unemployment wasn't horrible, but it took much longer to recover. 9/11 occurred, and at that time, we were already starting to see an economic decline. If you look back, we were starting to talk about a recession, and then 9/11 took place, and it created like a step function in the decline. So I don't credit 9/11 for the economic situation at the time, but it just took it to another level. We were already on a decline. And today, look at this. We've been in this recession since 2008 or before, and we're still trying to recover. And so what do we need to do to get back on track? And who needs to be in the conversation, and how are we going to do this? Just looking at manufacturing in the United States, since World War II, we saw, of course, industrial growth in the United States, where a large majority of our population was employed in a manufacturing-related sector. But since 1980, we've seen a drop at this level. And so that's why you hear discussions in Washington, D.C. about advanced manufacturing and how to redefine this industry space and how we need to educate our workforce. Then we have the grand challenges. Looking at big pictures of areas in sustainability, energy, water, and how we do education, personalized learning. So we have a lot of things on the table right now. Then we talk about 21st century skills. So before we talk about education, when we need to get kids in the math classroom, in the science classroom, we need to talk about elementary school, where we need to try to engage students at that in science and math. But there are a whole lot of other areas like technologies advancing at such a rapid pace, and how do you integrate that into the discussion? And then there's just an infinite discussion about creativity and innovation. But we look at the federal investment in science and engineering education. And last summer, when I was here before, we were in the middle of completing just a humongous survey for the federal government to see all the programs by which we're funding grants to universities to see if there's any duplication. And I applaud that effort, and it was difficult. But the interesting thing, we found out that innovation requires engineering. I'm an electrical engineer, but less than 1% of the annual investment is targeted to engineering education. And so there's a disconnect. And so for some of you in the audience that are able to have a conversation with your representatives, that might be an interesting topic. So I like to disaggregate STEM and look at what we really need for the future. So the investments are on this relative scale. Now, where is computer science in all this? Computer science spans all the STE&M in this discussion. So the funding for computer science is very important right now. We have a severe workforce shortage in computer science. And so just keep in mind that it spans all of these letters. Now we talk about the pipeline, and I'm starting to talk about the funnel. So we have the K through 12 community, and I have disaggregated numbers by gender and underrepresented minorities. So in this country, we talk about African Americans, Hispanics, Native Americans, and other groups. But as the K through 12 community starts through the education pipeline or the funnel, we see people dropping out of this sector. So just looking at the total workforce here, we have a small percentage going into these areas required to talk about innovation. But what about the future inputs? Well, if you take a look, I like to look at pictures because they make you look at the challenge head on. So this is Prism magazine from ASEE, the January issue. And here is a picture of young children who will graduate from high school in 2020. How are we going to develop these students for lifelong careers? So I think we are at a tipping point. We have funding, we lack engagement of students, and we have the rapid development of technologies. We have a recession that's global in scale. So how do we take a look at this challenge? We have to look at the people we're developing. When we talk about the pipeline, we tend to assume, especially faculty, that students are going to go from elementary school to middle school to high school and then to college. But for, I would say, 3/4 of the population in this country, that doesn't happen. There's not a linear path through college. And so if we do not really pay attention to our human resources, we are never going to recover. So I really like this quote from Sir Ken Robinson. It's out of one of his TED presentations. You really have to look for human resources. They're buried deep, just like natural resources, and we have to figure out how to mine people. Okay, so who's in our classroom? You may be a professor at a university like Stanford. I graduated from Georgia Tech. I'm a faculty member at Texas A&M. These are Research One universities. We tend to see a large percentage of our students go through that linear path. But in some of my classrooms, I can see someone in middle age. She may have stopped to raise a family and then come back to school, or a person that is physically disabled, or we have a person that stepped out of the pipeline to go serve for our country. We may have had, here are some young geniuses here. How do we nurture their high intellect to contribute in a mature way? So who is in our classroom? I have taught classes where I had veterans. One of my PhD students is female. She came back to school after working in industry for a number of years, raising 5 children. And she finished her PhD at the age of 44. And she was single. And now she's a senior scientist at Battelle. So how did I supervise her as her PhD advisor compared to somebody that was, 26? I had to do it differently. This is interesting, I thought, out of the Austin, Texas newspaper recently. 7 in 10 children under the age of 1 today in the state of Texas are defined to be minorities. And yet when you look at our science and engineering workforce, we have low representation of these individuals in these professions. And if you look at, this is from the same article, if you look at a snapshot of different states, we are looking at very high percentages, but we're not getting them through our educational system. And then there's the issue of poverty. So my son, I will say, was privileged. I was able to pay for his college, thankfully. He just graduated from Stanford in computer science. He went the linear path. But many of our students don't do that. Some are just finding the next meal. And if you look at these percentages here, it's, I think, eye-opening. So these are the current 2010 demographics on socioeconomic situation in the United States. So how do you teach a student, how do you engage a student in elementary school who's concerned about where his or her next meal is going to come from and keep them engaged? I have a hard time studying when I'm hungry. And this is a reality, but look at this. Along the borders, the dark colors are the areas where you have 31 to 56% poverty levels. And then you have a global issue. And we know about some of these countries across the globe. And so in the era where we're talking about global education and partnerships, just like we are in this room, how do we stay cognizant of the realities? So let's look at some opportunities here. One of the major programs in my division is called the Engineering Research Centers. This program has been around since 1985. It was launched after an important study by the National Academy of Engineering, where back in the 80s, we were looking at the semiconductor industry moving offshore to Japan. So that was what was going on at the time. And so the ERC program was required to get launched at NSF, and it's in my division. It's been going very strong for 27 years now, keeping its core values to enhance competitiveness and to prepare our students for the future, to contribute to society. But the premise around it is to look at an engineered system, a challenge at the systems level. It's not like, oh, I'd like to develop new electronic packaging technology so I can encapsulate, nanoelectronics so I can plug into something. We step back in this program and look at a big problem and look at the expertise that's required to address the problem, with education as a primary focus in the whole discussion. These centers are required to be multi-university. You have to have stakeholders at the table. We do evaluate them every year with an external reviewer team that comes in to the lead university, and we evaluate everything: the research, the education, the demographics of the participants, the tech transfer policies, et cetera. But industry is required to be at the table, and they help the faculty define the nuances of the grand challenges around an engineered system for the center. So I wanted to start here to say that these are the drivers. Then within the universities, we're looking at student leadership teams. The students are just amazing. They are absolutely amazing. They're natural leaders. They talk to each other across the universities, and they engage with the faculty in really interesting discoveries. And then the center is responsible to outreach to the rest of their partners and industry and try to inform the government about important issues. So let me just show you a couple of centers as a highlight, because I have a suggestion at the end where SRII can perhaps play a role. We just awarded this center last year to Stanford, who is the lead university with Berkeley, Colorado School of Mines, and New Mexico State. When you look at an aged infrastructure like our water system, these systems were developed decades ago with the technologies that were around at that time. But the urban areas have grown dramatically such that we have challenges where the technologies are energy drains, we have pollution, we have water shortages, et cetera. So this is their system level challenge. And through these selected partners, because of the expertise that they have, this is what they're driving toward. Energy positive systems, where a water system can actually contribute to the energy for the environment, resource recovery. And you can see here that we have a lot of policy issues and regulatory dancing that we have to do. But if you see some of these technologies in here, you have sensors, you have computer networks, et cetera. Everything is smart. And so when you're looking at a group like this one, SRII, IT could strongly enable the future of the water system. And in fact, I told this center about this organization and perhaps to start a dialogue. But look at the grand challenges of our infrastructure, and this is the same in every country across the globe. And they do have international partners, and they're going to really try to achieve this objective in 10 years. To do that, this is the strategy, and this is one of those charts where I don't want you to get a headache trying to read it. But the strategy in each of these centers is that this is where the faculty reside. They want to do research in their own little lab. They want to publish papers with their students. But what's driving this whole center are the stakeholders and the system test beds. And so when you have experiments going on at this level, that's going to inform what we need to do at the fundamental level. So, if you develop a new material or a new device, but, it doesn't mean anybody's going to care. And, you may publish 5 papers, but the question is, who cares? So, when you're looking at a real major challenge at the systems level, this will inform the research that needs to take place. You take this research out of the lab, and then you have some lab-scale test beds. That also informs the research, and that's what these feedback loops are. And then the industry at the table will watch everything that's going on here. And look at these areas here that enable the translation from the lab to a laptop test bed and all the way to a full system. And so this is a continuous feedback loop and a real challenge for the director to try to herd all of these cats to solve a big problem. Another center we just funded, which is 50% co-funded by the Department of Energy, is the center led by the University of Tennessee. Again, this is an opportunity for a group like this. When you're looking at smart grids, where you have smart meters installed or renewable sources of energy, and the challenge that you have 3 major regions, of course Texas has to be off on its own, that's just the way they are, and you're trying to create, say, like an interstate highway system, but for the grid. So you not only have technical challenges with devices, you have to integrate devices renewable sources of energy together with the existing sources of energy, like the coal-fired power plants or nuclear plants, et cetera. And so how do you integrate all of these sources of energy into a grid and optimize the system? IT is completely threaded throughout this whole challenge, from the device level all the way up to the intercontinental system. Who owns the data? We have big data here. Who owns the data? How do we mine the data to make smart decisions? What happens during a blackout? Et cetera, et cetera, et cetera. So this center has a big challenge. So they do the three-plane chart, they're required to. The beauty about this construct is that you have to explicitly identify the barriers that will take you from one level to the next. And let me say that again. The center is required to explicitly identify the barriers to go from one level to the next. And when you look at your barriers head on, then you really sit back and say, okay, you know, it may be fun to develop that nanostructured material over here, but is it really going to address any specific barrier? So this is a real big challenge. So again, I want you to focus here as well. I won't go into their three-plane chart, but as you can see, they were successful in the competition because they were able to map out what they had to do to address a grand challenge. So my question here, here's an opportunity, and this is something I'm trying to work on at NSF in partnership with other directorates across the building. What if we're able to establish a program that's like an engineering research center where you have a grand challenge around education? And what are the right questions we need to ask? It's not just course content. We need to look at the big picture and see what are the real questions we need to ask and what are the barriers to address them. And you also have, you have cultural differences. I showed you that collage of individuals with different backgrounds. So you have cultural differences, you have socioeconomic differences. Any organization is going to have its behavioral challenges. I mean, just look at faculty. The innovation ecosystem, how do we effectively transfer the developments from the universities into industry? Another partner we tend not to talk about are the nonprofits. And one thing I've learned is that nonprofits have a lot of money, and we've not put them at the table as much as we could. But in the United States, we have 50 states. So we have 50 state boards of education. Then you get down to the local level, and you see a big challenge here. So if we talk about computer science education or STEM education, we have a challenge in looking just in this country at the 50 different states and all the local communities that are running their school systems. So right there is a system in itself. So if we were to develop this three-plane chart for an education system, what would it look like? What's the fundamental work we need to address here? What are the barriers? For example, say a faculty member is developing new course content. How is that course content going to make an impact? Or if another faculty member is looking at some human-computer interaction type of strategy for education, or you have a neuroscientist studying how the brain works and learns. Fundamental stuff. But what are the barriers to take those research results and actually inform and impact education? This is my challenge to this audience. We have no principal investigators who have yet defined this big scale problem. But I do think education is a systems problem. So the stakeholders, once we figure this out, we also have to be able to translate these results to the classroom or to industry or to some other stakeholder. And that way we can enable innovation. But how do we get through this challenge here? This is documented. We have people looking at engineering education research. Of course, I say engineering, that's my division, but you can apply this all across STEM or any type of education. But we can talk about an innovation cycle around education. So, So this is published in a paper out of ASEE, the American Society for Engineering Education, where you're looking at education research and you're trying to put it into practice. This is a big challenge. So you see a lot of papers published here, you see a lot of papers published here, but you see very little in offering suggestions on how to take research into practice and how to take lessons learned from practice to inform the research. So my question is, let's think about this three-tier chart idea. So from my perspective, we want to develop new engineers for the future. So it's not only their coursework, but they need to demonstrate leadership and creativity. And within the Engineering Research Centers program, we are required, the centers, to look at teaching students to be innovators. It's a requirement. It gets evaluated every year. So we talk about an innovator DNA. So this is not a new idea to the ERC program, but the centers program has yet to tackle the education system challenge. My division, along with another division in the foundation, we just funded a $10 million center led by Stanford. It's a national center to look at innovation education at the undergraduate level. It's led by Tina Seelig. Some of you may know her. She is aggressively trying to pull together resources and also establish a web portal for all the colleges of engineering across the country to have access to a repository of best practices in innovation education. So some of it could be course modules, some of it could be projects, and so on and so forth. So if you want to know more about this center, it's a year old now, and she can inform you about what they're doing. It's, again, they're rethinking the entire engineering education process to look at engineering, education, and entrepreneurship. So my final slide is a challenge. Back in the 60s, 1959, well, Sputnik was in what, 57? JFK challenged the country to think differently and not to be afraid of the hard problems. Those are the ones we need to tackle. I still think his words are very important today, and I offer them to you once again so we can look at education in a realistic way. And so with that, I'll conclude and be happy to answer any questions.